As I mentioned in the last video, Eulers are really simple conceptually, but in practice, they're often complex and confusing. By contrast, quaternions are conceptually confusing, but in practice, they are shockingly simple and gotcha-free to use. But indeed, explaining how quaternions function on a technical level is going to be a little bit tricky, so bear with me. I'm first going to give a quick overview of some of the benefits of quaternions, and why I like to use them in my rigs. Then I'm going to give a technical explanation of how quaternions represent rotations. And finally, at the end, I'm going to give you a simple, intuitive mental model of quaternions that I use when I'm animating. So, what's so good about quaternions? Well, first I'm going to tell you one circumstance where you never need to use quaternions: single-axis rotations. There's no reason to ever use quaternion rotations for controls that only ever rotate on one fixed axis. It's pointless. For those, use Euler rotations. And similarly, for two-axis rotations, Eulers are often a good choice as well. But where quaternions really shine is with full three-axis rotations, and here's why. First, no gimbal lock or changing axes, which are a big issue for Eulers. 2, rotation interpolation is smooth and direct, which is often not the case with Eulers in the general 3D case. And 3, there are several things that are trivial to calculate using quaternions that are a pain to calculate with other rotation representations, and these are things that are actually useful for rigging. Points number 1 and number 2 are directly related to each other, and I usually think of them as being the same thing. When we rig full 3-axis rotations using Eulers, we have to be careful about what rotation order we pick, to minimize the possibility of gimbal lock situations and strange axis changes. By contrast, quaternions never have gimbal lock issues, and always interpolate between rotations in a consistent way. Recall that when I was discussing axis angle rotations, I mentioned that for rotations, the equivalent of a straight line, the most direct path between two positions, is a rotation around a single axis. Well, it turns out that interpolating between two quaternions always takes this straight line path. And moreover, the nature of quaternions means that whatever interpolation scheme we choose, be it linear, Bezier, or anything else, it will behave consistently and predictably when interpolating. And this is no coincidence. Quaternions represent 3D rotations not as a rotation path, like Eulers do with a sequence of rotations, but instead, as we'll see in a moment, represent them more like a rotation delta. And that gives them very stable, consistent interpolation properties, because they're not backtracking through some arbitrary rotation path that has nothing to do with what the animator is animating, which is precisely what happens with Eulers. Due to the way quaternions represent rotations, it's also trivial to find the opposite of a 3D rotation, which we'll be using to rig the 3D ball, and to find the minimum angle or distance between two orientations. Both of these are useful to be able to do in rigging. So there we have it. Those are pretty much the advantages of quaternion rotations. But how do they actually work? What do those numbers mean? The first thing that usually throws people off about quaternion rotations is that they have 4 numbers instead of just 3, typically written as W, X, Y, Z. People usually wonder, what does that 4th number, the W, mean? Well, the answer is that it means the same thing as the other 3 numbers. That's not a very helpful answer, I know, but it's basically true. There isn't anything special about the W. The X, Y, and Z have the same bizarre meaning. The only difference is that we consider 1, 0, 0, 0 to be unrotated. But we don't have to. We could consider 0, 1, 0, 0 unrotated, and then X would be the special number. Okay, so this is probably pretty unhelpful so far, but I want to make sure you understand that there isn't some special different meaning that W has compared to the other numbers. It's not like axis angle where W is the angle and X, Y, Z are the axes. No, with quaternions, all of the numbers do the same kind of thing. But what is that? What do they do? To explain that, I'm going to show how quaternions work in 2D just for 2D rotations. The way they work in 3D is just a simple extension of that. So the basic idea is this. With Euler and axis angle rotations, we specify angles, right? Say our starting orientation is here. Then a rotation of 45 degrees would put it here. And that only takes one number to represent, one simple number, the angle. But remember back when I was explaining orientations, I pointed out that we could represent them with a point on a circle. Now, bear with me a moment because I'm about to explain something that's not quite right, but it's a stepping stone to understanding quaternions. Don't worry, I'll correct myself momentarily. Okay, so quaternions basically do exactly that. Instead of specifying an angle, we give coordinates of a point on a circle. So for example, say our vertical axis is w, and our horizontal axis is x, and we plot points as wx. Then unrotated would be 1, 0, up at the top of the circle. 90 degrees would be 0, 1 at the side of the circle, and 45 degrees would be approximately 0.7, 0.7 on the upper right of the circle. So you can see that this isn't actually that hard to understand. Although this isn't quite right. Quaternions do something really close to this, but not quite. So here's the correction. What quaternions really do is they take the angle you would get from the system I just described, and they double it. So for example, instead of 45 degrees, you get 90 degrees, and instead of 60 degrees, you get 120, and instead of 180 degrees, you get 360. So this is a little bit confusing, but you can get the hang of it with some practice. Just imagine where the point would be on a circle, and then double the angle you would get from that. So let's try it out in Blender. We have this monkey head, and its rotation mode is set to quaternion. As we rotate it on one axis, say 90 degrees, we see that the values relevant to that axis shift approximately to 0.7.7 as we predicted, because 0.7.7 is 45 degrees when plotted on a circle, and the double of 45 degrees is 90 degrees. And as we approach 180 degrees, the axes shift to 0, 1, also as we expected. And this works for the other axes too. And I can take this even a step further. On another layer, I've set up a weird little rig. All it does is take the location of this empty and plug it into the quaternion values of the monkey head. As I move the empty around, you can see that the monkey head rotates twice as much as the angle the empty creates. Wild, eh? Okay, so that's all well and good for 2D rotations, but how does it work on multiple axes for 3D rotations? Well, when we're only rotating on one axis with two numbers, the quaternion is a point on a circle, right? Where this is unrotated, and this is rotated 180 degrees. When we're rotating on two axes with three numbers, the quaternion is a point on a 3D sphere, where this is unrotated, this is 180 degrees around the x-axis, and this is 180 degrees around the y-axis. And everything else is smoothly blending between those rotations. For example, this point, halfway between these 2 points, represents the orientation exactly halfway between 180 degrees on x and y. And this point, equally distant from all 3 of these points, is a precise average blend between them. Looking at this, you can start to get a feel for why quaternions interpolate so nicely. And finally, when we're rotating on all 3 axes with 4 numbers, well, human intuition falls apart a little bit because the quaternion is now a point on a 4-dimensional sphere. But don't worry, the mechanics are exactly the same as the single axis and 2-axis case, it's just extended to one more axis. All the same rules still apply. So you may be wondering, why do quaternions double the angle? Why not just leave it alone? Well, let's take a look at the 2-axis 3-number case again. What would happen if these 2 points represented 90 degrees around the x and y axis instead of 180 degrees? Specifically, what 2 points would represent 180 degrees around x and y? Well, let's try x first. Intuitively, we would just keep following the circle to the bottom of the sphere, right? Okay, cool. So that point now represents 180 degrees around x. Now what about y? Well, let's follow this circle down to... oops. The bottom of the sphere. The bottom of the sphere appears to represent both 180 degrees around x and 180 degrees around y. But that doesn't make any sense at all. If you rotate something 180 degrees around x, or 180 degrees around y, you would get very different orientations. So we need them to be different. However, if we switch these points back to being 180 degrees, then following these circles gives us 360 degrees around x and y at the bottom. And guess what? Rotating something 360 degrees around x, or 360 degrees around y, results in the same orientation. So it works out. And this doubling of the angle actually has a side benefit. Quaternions can represent 720 degrees of rotation, not just 360. This property of quaternions is commonly referred to as double cover, and it allows us to do things like find the opposite of a rotation simply by making W negative. It also means that if an animator has made two keyframes, say one here and one here, but is interpolating the wrong way, he can simply flip all of the components of one of the quaternions, and then it will interpolate in the other direction. One last thing to note is that technically speaking, quaternion rotations are only defined for points that are precisely on the surface of the sphere. Or, to take a look at the 2D case again, if we put a point out here, it doesn't count. Only points that are exactly on the circle count. This is one of the reasons that a lot of software, like Maya and Softimage XSI, choose not to expose the actual quaternion components to the user. If the user can freely manipulate the quaternion coordinates, then they can put the coordinates in all kinds of illegal places. Blender, however, does directly expose the quaternion components, which I think is kind of nice, and what Blender does for coordinates that are not exactly on the circle, or sphere, is it interprets them as if they were projected onto it, like so. The only point this doesn't work for is 0, 0, 0, 0, in which case it defaults to some weird orientation, which isn't really a big deal since you never hit 0, 0, 0, 0 unless you're intentionally trying to. So there is actually one other reason why a lot of software doesn't directly expose the components of quaternions, and that's because of something called slurping and squatting. What on earth are those? Those are kind of weird names for stuff. Well, remember how quaternions always rotate on a single axis if you interpolate between just two quaternions? Well, a slurp, or spherical linear interpolation, is a further restriction on that, where not only does it rotate on a single axis, but it does so at a constant angular speed. It turns out that the math for this for quaternions is pretty straightforward. A squad is something similar, it's just that it's for a smoother interpolation, quite a bit like Bezier interpolation. Unfortunately, enforcing proper slurping and squatting requires that the software limit certain things about how quaternions work, and these are limitations that cannot be enforced if the actual curves of the quaternion components are exposed in the animation curves editor. And this is another reason why, for example, Maya and XSI do not let the user directly tinker with quaternion components. It gives the software a chance to do these nice types of interpolation. Blender takes a different tactic, which, in my opinion, is the better one, and just uses the typical interpolation techniques to directly interpolate the quaternion components. This gives the user free rein to control how their rotations are interpolated, but it also has a drawback. Let's revisit the 2D circle once more. Let's say we're trying to interpolate between this angle here and this angle here over the course of 5 frames. A slurp would do a nice constant speed interpolation over the part of the circle between them, but a straight linear interpolation of the coordinates, after being reprojected back onto the circle, would be a bit slower towards the beginning and end, and faster in the middle. This is the drawback to exposing the quaternion curves and interpolating them directly. However, notice that this is really more of a problem for interpolations between very different rotations than it is for rotations that are closer together. In fact, even for rotations as large as 90 degrees, remember quaternions double the angle, the issue is hardly there at all. So in practice, this usually isn't a big deal. The animators simply insert 1 or maybe 2 additional keys for large rotations. So this is all well and good. Quaternions are pretty cool. But there is a downside to quaternions, which is that they are generally harder to grasp conceptually than Eulers. This isn't such a problem for us riggers, who only deal with quaternions on a technical level anyway, but for animators, who should be focusing on the art and not the tech, it can make quaternions quite intimidating. Fortunately, there are a couple of ways to help animators out with that. The first is to tell animators to just ignore what quaternions mean and just treat them as some abstract representation of rotations. This is actually how I worked with quaternions when I was animating on Big Buck Bunny. Instead of worrying about tweaking animation curves and all that, I just set extra rotation keyframes to define things like ease in and ease out and sharp changes in rotation speed and direction. And because of how nicely quaternions interpolate, this actually works out really well. The other way, which I use now, is to think of quaternions as mixing orientations. Kind of like color, where we're mixing red, green, and blue, except in this case we're mixing 4 orientations. one that's unrotated, one that's rotated 180 degrees around X, one that's rotated 180 degrees around Y, and one that's rotated 180 degrees around Z. But the principle is basically the same. The hue of a color is determined by the ratio of red, green, and blue in it. 1 part red and 1 part green makes yellow, and 2 parts red and 1 part green makes orange. Similarly, the orientation of a quaternion is determined by the ratio of the 4 core orientations we mix in. 1 part W and 1 part X is an equal mix of W and X, so the orientation is exactly halfway between them. 1 part W and 3 parts X has a lot more X in it, so it's going to be closer to X. What's great about this mental model of quaternions is that it's actually extremely close to how quaternions really work. The only thing it doesn't account for is what negative values mean. But that's easy to tag on to the mental model. Negative values merely rotate the opposite direction when you mix them in, but they're still mixing towards the same orientation. They're just going the other way around to get there. And in fact, that gives a really good intuition for why flipping a quaternion, or in other words, flipping the negative signs of all of the components, will make it interpolate the opposite way around. It's because all of its components are mixing in the opposite rotational direction. Anyway, so yeah, that's the mental model of quaternions that I use when I'm animating. I think of quaternions as being like mixing 4 different colors of paint together, except instead of colors, it's mixing orientations in space. And honestly, in a lot of ways, quaternions feel more artistic to me than Eulers do, because it's like mixing paint. Yeah.